Welcome everyone to our session on QQIs, a powerful new tool for use with magnetic particle inspection. The parts you've been looking at represent just a few of those inspected every day. As inspectors, you face the same problem each time you're handed a new part. Should I use a head shot, a coil shot, or both? How much current should be used? Larger or more complex shaped parts might require 3 or more magnetizings to assure that all critical areas are free of defects. Landing gear forgings used on jumbo jets and some large nuclear parts can require as many as 8 separate shots and inspections. Wouldn't it be great if each new part we were asked to inspect had a minimum, that is, a borderline size crack in each critical area? During the next few minutes, we are going to demonstrate how artificial flaw shims, QQIs, can take the guesswork out of setting up for almost any part you must process.
Do the QQIs take the place of the pi gauge or the Hall effect meter?
No, not at all, Arlene. Each inspection aid has its pluses and its limitations. QQIs, unlike the pi gauge, may be placed anywhere on a part, including tight radiuses, and several may be placed at one time. The clear visual indications produced on a QQI are more operator-friendly than readings by a Hall effect meter. Plus, they are the best way to assure balanced fields and multidirectional magnetizing. Now let's take a close look at a QQI.
QQIs like this one are sometimes called artificial flaw shims or paste-on defects. Their permeability is comparable to most grades of common steels, so when they are pasted on magnetizable parts, the magnetic field generated in them by the magnetizing force is very comparable to the field generated in the part beneath them. This particular QQI, the most basic shim, is only 2/1000ths of an inch thick. The defect you see, the circle and cross, are precision etched to about 1/3 of its cross-section. That's about 15 microns. This miniature version is designed for small areas or for tight part radiuses. They are applied defect side down to prevent possible particle buildup within the flaw with repeated use. They can therefore be used over and over again. They may be held on the surface of the part by hand, held down on the part by their edges using Scotch tape, or may be pasted onto the part using superglue for repeated tests. They are used to confirm that a magnetic field is present at all critical locations on a part and also indicate its direction. When affixed to a part, they share the flux field with the part being magnetized.
Most important of all, QQIs are operator-friendly. Readout is an indication right on the test part. There are no scopes or meters to read and interpret. QQIs have 3 primary uses.
1, they keep the number of shots each part must receive to a minimum. This keeps the production manager happy. 2, they provide each inspection team with exactly the same sample part for every production run, containing minimum size defects in every critical area. It may be run as needed to assure that the entire inspection setup is doing its job. This keeps the quality manager happy. And 3, they're a great training aid for new inspectors.
Let's demo QQIs in action. First, for the production manager. This part has 2 critical areas where any crack, regardless of direction, must be detected. We will use a multi-directional magnetizing unit to process it, so only 1 magnetizing and 1 inspection is required.
Since we're only going to process this part a few times in order to balance the 2 required fields in the part, we'll use Scotch tape to keep the QQIs firmly in place. Let's tape down all 4 sides of our QQIs to keep them from flexing when we magnetize. We now set the contact and coil current levels based on our best guess using formulas and past experience.
We are now ready for our first try. Do we have enough head shot and coil current to bring out defects in both directions in all critical areas?
For the QQIs to work properly, we must use the continuous method. You should also know that whenever we use multidirectional magnetizing, the continuous method is also a must. Looks like too much coil and not enough contact. Now the fields are balanced. The correct current values are 800 and 1400 for this part.
QQIs are also excellent for reminding us where the field in a part cancels out if the part isn't magnetized properly. Yoke-shaped parts like this one are very likely to have a dead area if we do not use a double headstock. Now let's demo QQIs in action for the quality manager. This time, we will be creating a system performance sample to be processed at the beginning of every production run. Let's use super glue this time instead of Scotch tape.
First, we use solvent and a rag to remove any oil or dirt from the area where the QQI will be glued. Gel-type superglue is less messy and more convenient to use. It's best to hold a QQI with masking tape to avoid superglue touching our fingers. After the QQI is applied, defect side down, we press it down and use a damp rag to remove the masking tape. Be gentle. If you push too hard on a rough surface, the QQI may be distorted and ruined. Wait about 15 seconds and then wipe the surface of the QQI with the wet rag to remove any excess glue.
Our QQI is now firmly affixed to the part. Should we ever wish to remove it, however, solvent will do it. If carefully done, it can be reused. Tom, I've set up our multi-directional unit for our part. Would you run it for us using the continuous method?
I'll be happy to.
By affixing QQIs to each different shaped part being produced, the inspector has a reliable setup sample for every production run. The test part assures overall system performance by checking 1, proper bath application, 2, correct bath concentration, 3, proper magnetizing, 4, that there is adequate black light and not too much white light, and 5, that the part is being run by the continuous method.
The indication on the QQI is great, and I see other natural defects as well. What would happen if we use the residual method?
Let's try it. Wipe off the indication and reapply the bath. Now what do you see?
I see a natural defect which came out due to the part being retentive, and also a weak indication on the QQI. Holes in the part must be causing the QQI to show residually.
What did we learn from Tom's experiment, class?
The coil shed on the multi-directional unit must have been last.
We found that weak residuals can sometimes show on our non-retentive QQIs if our test parts end up with a longitudinal field in them.
We found that it was necessary to use the continuous method with the multidirectional magnetizing and also when using QQIs.
Very good, everyone. Any questions now about QQIs?
I've heard that the QQIs are a flux-sharing device, so they will only have an indication when applied on an iron or steel part. Is this true?
No, Peter. This is a common misunderstanding. QQIs respond to any magnetizing force applied to them, H on the hysteresis curve, even from a copper central conductor bar or in air as with a coil. They can't tell us about B, the flux density in the part. Thus, they will show an indication when processed in a magnetic field with no part present, just like a pi gauge. But when used on parts of high permeability, like iron or steel, the indication on the QQI is related to the field in the part.
Can QQIs be used on induced current applications?
Yes, as long as the continuous method is used. Remember, QQIs will not show residually with circular fields, such as the toroidal field developed in an induced current shot.
Was that long torsion bar processed on a multi-directional machine using the yoke technique?
Yes, Peter. In the past, such applications were limited to parts less than 40 inches long. But as machines have been improved, this technique may now be used on much longer parts. And with QQIs, we don't have to guess. We can verify the field even in the middle of that long part. That concludes our session on QQIs in action. Thank you all for coming.